everyone, depending on where you are. Welcome to the second Princeton Review AP Chemistry live stream. Today I'm going to be giving you guys a little bit of a refresher on some of the stuff we talked about in the first live stream, and you guys can find that on the Princeton Review's YouTube page, talking about some of the changes to the AP exam that you can expect. Also going to start talking about, and we're also going to be talking about some more science. So some of the topics that we didn't get into last time, we'll be covering today. So just a brief intro, and if you're more interested in any of the introductory stuff, you can go back and take a look at last week's live stream in which I did a little bit more of this. I'll have a little more science today. My name is Brad Hutnick. I teach, I tutor, I train, and I develop content for the Princeton Review across a variety of tests, but all within the general and organic chemistry realm, and so AP Chemistry definitely falls under that. Different pictures of the kids and dogs and a cactus from last time. You can go back and get more detail on those if need be. This is the same introduction that was in the previous live stream. I just want to go through this briefly in case you weren't able to make that one. But I encourage you to take a look at that for a little bit more detail. I also encourage you to take a look at this website here for the most up-to-date and detailed information about taking the AP exam and the changes you can expect going into this 2020 exam. The biggest change probably is that the test date itself has changed. I believe it used to be May 7th. Don't quote me on that. It's now May 14th. Going to be starting at 2 p.m. Eastern time, or you can figure out what time zone you're in though on your own. The system is going to be all online, and it's going to be important that you access the system about 30 minutes early. You really want to make sure you get in and make sure everything's working. Just as I was trying to enter the interface here, I started to try to enter it a few minutes too early, and it wouldn't let me, and I really panicked. You don't want to have that panic set in before your AP exam, so you want to make sure you're there early enough to make sure you avoid any technical difficulties. If you do have technical difficulties that completely prevent you from doing it, or some sort of illness or something like that, there is a makeup date, June 2nd, but let's hope you're going to be able to get this taken care of on May 14th. The format of the exam has changed dramatically. There are no multiple choice questions anymore. The AP exam this year is going to be 2 free response questions that are weighted about 60-40 here. The first question is going to be 25 minutes. The second question is about 15 minutes. So you can expect the first question to be, fairly significantly longer and maybe a little bit more difficult as a result than the first. The questions themselves, the AP, this is all from the AP website, by the way, they specify that it's similar in structure to a long free response question on the traditional AP exam. So I doubt that the format of the questions will have changed all that much, but they do make a point of saying here that these are similar in structure to those long exams. After you take each of the questions, you'll have a 5-minute period in which you should upload your response to that question. The format of the AP, you're going to be able to either type responses or write them by hand and then take a picture of them and send that off for submission. I think it depends a little bit on the type of question. Typing would be really difficult if you have to write out chemical equations or mathematical equations. So that's probably not my preferred method. I would probably tend more towards writing these out by hand and then taking pictures of them. And that's probably something you're comfortable with doing, writing it out by hand, at least from having taken a bunch of other exams by taking a bunch of other exams and writing them down, as opposed to having chemistry exams where you end up typing the answers. That's probably pretty rare. So you may be more comfortable with the handwritten response. Once you finish and upload question 1, you can't go back to it. So if you realize that you didn't balance the equation correctly, once you're in question 2, unfortunately, it's going to be too late. So Claire is asking a question, and by the way, I should have mentioned Tile is going to be in the YouTube chat talking to you guys and sending questions over to me, so please feel free to ask any questions in there. I'd be happy to help out. Brian is also here helping out with the technical side of things. So Tile sent over a question from Claire. She's asking, will we need to type formulas or show work to questions by typing? I think the typing formulas is really difficult. You'd have to you'd be dealing with subscripts and superscripts. It gets really messy and gets really tedious. So I think that the best thing to do would probably be to write out any chemical equations or formulas or anything like that. You're also saying we need to show work to questions by typing. I'm not sure exactly what you mean by that, Claire. If you mean that, if you're asking about maybe supplementing handwritten with typed, I don't believe that's going to be the format. I think you do have to stick to one or the other. So Claire, I hope I answered your question. If I didn't, please ask Tile again, and we can maybe figure it out a little bit better. This is another big change in addition to the date and the elimination of the multiple choice questions. The AP exams in 2020 across the board, except for one, I think is going to be open book and open note. I made this same point last time and I'll make it again. Just because you have open book, open note, open internet, open Google to find out information, that doesn't mean this exam is going to be easy. In fact, if anything, if I'm making an open book exam, I would probably make it a little bit harder on students because they do have that safety net to help them out, right? So you really need to prepare for the exam on your own, pretty much the same way you would have prepared for the traditional administration of the exam, which doesn't include the open book, open note aspect. So I think it's important that you're comfortable with everything going in, that you don't have to rely on these sheets, right? You don't have that much time to go through these questions. If you're having to spend a lot of time flipping through your book or Googling things or looking through your exam, looking through your note sheet, you're going to find yourself very short on time, most likely. So I'm seeing a couple of questions here. The architect is asking, where would one upload the answers? I'm not personally taking the exam. Where would one upload the answers? I don't know the answer to that tile. Sorry, the architect. That would be done through the AP website, presumably, and I don't have access to taking the exam, so I'm not exactly sure what the interface is going to look like. But presumably on the day, that will hopefully be sort of obvious to you. Hopefully there'll be a big red button that says "Submit Answers here" along those lines. CJ is asking what notes I would recommend to use for the AP exam. So I've written out a couple of things here that I think would be good for you to have on a sheet to have handy, in addition to your textbook and maybe the notes that you took in your classroom in your classroom class over the year. Some things that I would include on a sheet that maybe you want to have for quick reference: annotated equations from that equations and constant sheet. It's great that they give you this equations and constant sheet, but sometimes it's a bit of a mystery. So I think it might be helpful to mark up what those equations mean on there, and we'll talk a little bit about that later in one of the topics, the scientific topics we're going to be talking about. People's names and contributions. It's not worth memorizing, that it's Heisenberg's uncertainty principle. It's important to know the uncertainty principle, but the fact that Heisenberg thought of it or whatever is not the important part, right? And so I would write down names to go along with that in case they just happen to ask of one of them. Periodic trend arrows, showing how the different periodic trends are going to change over the course of the table. We talked about periodic trends in last week's live stream, so if you have some questions more specifically about that, you can go back and take a look. Polyatomic ion names and formula, that's just memorization, so that's good to have a quick reference. Same with Vesper geometries and hybridizations. Anything you struggle with, anything that over the course of the year in your AP class, you've just realized, I never get this right, I always think it's backwards or something, just go ahead and write those things down. The notes that you're going to be bringing in, right, they're just for you, and so you can make them as personally appropriate as possible. You can't cheat. Obviously, it's all honor system based, right? Telling you're not going to cheat, but they will be checking in certain ways. So they're going to make sure. One of the ways they'll be checking is they're going to take your work and they're going to show it to your AP teacher. So the teacher that has been grading your work all along will have an opportunity to take a look through your materials, and they may be able to raise some red flags, if they are worried about cheating. The second sentence here, right? Points aren't going to be available for information that you can just get in your textbook or from Google. If you need a molecular weight for the AP exam, you can just Google a compound's molecular weight, and it's probably going to deliver it to you in a special box up top. They're not going to give any points. My guess, at least, is they're not going to give any points for Googling something like that. So you want to keep in mind that the exam is still a hard science exam. It's not a how much can you read in your book exam. The book and the notes and the crib sheet you have are going to be great for facts, but you still need to be doing a lot of analysis by yourself. It's going to be hard to cheat on the analysis, certainly. So let's not bother opening that up and trying. In addition to your own materials that you would prepare ahead of time, you're also going to need a periodic table of the elements and the equations and constants sheet, like I mentioned before. I highly recommend having a hard copy of those. I think it's much better to have a hard copy to flip through rather than having to move around within tabs on your screen and accidentally closing the wrong tab. So I like having a hard copy of those. They also mention here that calculations probably aren't going to be the calculations you're going to be able to do with pencil and paper. So you probably won't need a calculator, but you are allowed to use a calculator. And I'm interpreting this last sentence here to mean that you can even just use the calculator on your phone. So no legwork is required there. Just a little bit of information and recommendation about how to prep for the exam. I already mentioned, take a look at the AP website to get the most up-to-date information, but mainly you want to be continuing your preparations about as normal. The format of the exam has changed, but the content and the content has changed a little bit, but it's not going to really change in terms of what you've been doing thus far. The some of the content has changed. We'll talk a little bit about that, but you're going to want to make sure you review the earlier chapters and topics from your AP class, stuff you did, months ago, holidays ago, a whole pandemic ago, right? So those things are a little bit maybe not fresh in your mind. So you're really going to want to review some of the early stuff. In addition, that early stuff will now be more heavily weighted because, as we'll see, there is going to be some information that has been excised from the exam. When you're practicing, you want to practice under actual conditions. You're not very far out from your exam now, so you really want to mimic it. Timing is really, really important. If you're taking an hour to do your free response questions, that's just not tenable for the exam. So you want to make sure that you are timed at this point. Multiple choice questions, right? There is no multiple choice on this exam anymore, at least this year, but they are still a great opportunity to practice content. So I really recommend that you continue doing those multiple choice questions. Along those same lines, go ahead and review your old exams, whether it's multiple choice, free response, whatever. Take a look at all the questions, not just the stuff you got wrong. Look at what you did right as well. And finally here, you want to make sure that you have a spot in your house to take the exam and that you figure that out ahead of time. Don't just wake up and figure it out on the day and just roll in right out of bed or something like that. You want to make sure you have a little bit of a plan in place. So I mentioned on this slide here, right? You want to review the earlier chapters because it's now more heavily weighted, or partially because it's now more heavily weighted, and it's now more heavily weighted because you can see down here these two red lines, units 8 and 9, acid base, as well as applications of thermodynamics, are not on the exam. The AP is sort of assumed that most people at this point in their class have not covered those last two topics, and so those are excised, which means that the first 7 units are now by proxy more heavily weighted. So you're going to want to focus more on this earlier stuff. In the first live stream, we talked mainly about material from these first 2 units. And this one, we'll be talking mainly about material from these middle 3 units here. We also touched on unit 3 in the first live stream. Note that these numbers here come from the multiple choice section, so don't put too much weight in those, no pun intended. But you can see here, intermolecular forces and properties we'll be talking about today is highly tested on the multiple choice section. There's a chance that transfers over to the free response question as well. We'll be talking more about those today. Okay, there's technical difficulty with this slide, so we're just going to move on through this. At this point, I'm done with the introductory period. We talked a little bit, a little review of what's on the exam, what's off the exam, and what big changes you can expect. At this point, we're going to be talking about science now for the remainder of the live stream, and we're going to talk about a couple of topics that I mentioned today: intermolecular forces and properties, chemical reactions, specifically one type of reaction, and then kinetics if we have time. If we don't have time, I'll try to roll that in to next week's session, which is going to be taking place on Friday, May 1st. Let's get into that first topic here, which is intermolecular forces. And the way you want to approach this for the AP exam is you need to know the different types of intermolecular forces, and you need to know what to do with them, how they work, what types of questions they could ask you about them. So we're going to run quickly through the different types of intermolecular forces. The first 2 here are highlighted in these green titles. So intermolecular forces, the first type in no particular order, I would say, are going to be dipole-dipole forces. And these are going to occur between polar molecules. Polar molecules, as you probably remember, have bonds in them with a difference in electronegativity. So they're going to have partial negative and partial positives, like you can see down here on this diagram of these 2 molecules of water. Anytime you have the partial positive sticking to a partial negative, that's going to be known as a dipole-dipole force. Positive of one is attracted to the negative of another. These intermolecular forces are going to be attractive forces. They're going to hold molecules together, right? Opposites are going to attract. Down below here, this hydrogen bonding, this is not a new type of force. This is actually a type of dipole-dipole. So it's a special type of dipole-dipole forces. So I want to write that on there. It's just a subset. Hydrogen bonds are a type of dipole-dipole force, and it is a dipole-dipole force or interaction specifically where one of the atom partners is a hydrogen. That's what makes this a hydrogen bond, all right? Hydrogen bonds are extremely special and extremely important. There's also extremely strict rules about when a hydrogen bond occurs and when it can't. And those rules have to do with what these atoms are right here. So we've got these two atoms, these two oxygen atoms involved sharing that hydrogen. And in order for this to actually function as a hydrogen bond, we need an atom like oxygen because it's highly electronegative. And that's going to give us this big partial negative charge here, right? If you had a carbon atom here, carbon hydrogen bonds are not polar, so you wouldn't be able to form a hydrogen bond because you'd be lacking the partial positive. So this oxygen is really integral towards the formation of this. In order for this to be a hydrogen bond, this could be an oxygen atom. It could also be a couple of other atoms. Both of these atoms need to be F, O, or N in order for this to be a hydrogen bond. Those are the three most electronegative atoms. They're the only ones that work. If this is a C, this is not going to be involved in a hydrogen bond. Fadi is asking, would you say a compound has hydrogen bonding or can form hydrogen bonding? That's semantics. I don't know that the graders are going to ding you too hard for that one. I would say that a compound experiences hydrogen bonding. That's usually how I would say it. Or it can form a hydrogen bond. I don't know about form hydrogen bonding, but that's a semantics question. It's good. You need to be precise with how you're speaking. I'm not denigrating it as a semantics question. So we get dipole-dipole, and then this subset of hydrogen bonds here. The other type of force we're going to be talking about, the other type of intermolecular force, is going to be London dispersion forces. Now, I'm not going to get into where these come from. It's a little bit strange, and you can take a look at a diagram or something in one of your books. But you just want to go into your AP exam really knowing the basics of this. The most important thing about these London dispersion forces here is they occur between all molecules. On the previous slide, in order for dipole-dipole forces to occur, you need to have a polar molecule. In order for an H bond to occur, you need to have this really specific set of rules here. You need to have one of those three atoms here. London dispersion forces, on the other hand, just occur between all molecules. All molecules are going to have it. It's sort of the intermolecular force of last resort. The rule about them is that more electrons are going to lead to greater London dispersion forces. Should also note here, for abbreviation's sake, for London dispersion forces, I'll just be referring to those as LDF if I need to write it out anymore. And they also, in addition to the electrons, they link this role of London dispersion forces to the molar mass of molecules, and that's really important. And we're going to see that come up in an exercise here in a second. I just want to clarify this a little bit. If we increase the molar mass, it's pretty much the same as saying we are increasing the number of our electrons, right? And we just saw up above, greater electrons is going to be greater London dispersion forces. So greater molar mass, which equals greater electrons, is also going to be approximately equal to saying greater London dispersion forces. All right, so molar mass plays a role. Whenever we're comparing molecules in terms of their intermolecular forces, we need to make sure that we're sort of dealing with an apples to apples comparison. Right here, the next part of this, they're talking about how to compare these, and they start off by saying for molecules with similar sizes. All right, so similar sizes is going to be important when we look at the example here. So we know what the three types of intermolecular forces are that we're discussing here: dipole-dipole, its subset hydrogen bonding, and then this very broad class London dispersion forces. They have relative strengths, and that's really important to keep note of here because we're going to need to rank these intermolecular forces to predict a whole host of molecular properties. So let's take a look down below here where they're saying for molecules of similar size, the intermolecular force ranking below can help you determine the relative strengths. The first and the strongest here is hydrogen bonding. That is going to be the strongest intermolecular force that you're going to come across, all right? So if you find hydrogen bonding in a molecule, you would predict that it would have very strong intermolecular forces. The second one here, non-hydrogen bond permanent dipoles, that's just those dipole-dipole forces. That's the very broad class, right? So B is the broad class, A is a very strong subset of that. And then finally, we get to London dispersion forces, which are known as temporary dipoles. These are by far the weakest. And again, they make the point, bigger molecules are going to tend to have stronger London dispersion forces as a result of having more electrons like we talked about up top here. All right. So you have the three different types that you would take into the AP, and you have their relative strengths. You really need to know that information. You need to go into the AP knowing these, because it's not the type, the ranking of these, which is strongest, which is weakest. It's not the type of thing that one would easily figure out, and it's certainly not the type of thing that one would want to waste time on going in during the AP exam. You would just want to know this order. So this is something that I think is good to have memorized. Now, when we're talking about intermolecular forces. Intermolecular forces show up in all aspects of chemistry, really across the board. Intermolecular forces are responsible for how we interact with nature around us. Anytime you're touching something, you're feeling intermolecular forces. And so it's really important in determining the properties of molecules. Specifically, one area that you might spend some time in is connecting intermolecular forces to phases and phase changes, right? As we go from left to right on this, right? As we go from the solid state to the liquid state to the gaseous state, what you can note about the arrangement of the atoms or the molecules in these samples is that in the solid state, they're very closely packed, right? They're very densely packed. In a liquid, it looks like this pile of atoms just sort of fell apart, right? And the molecules are starting to move apart from one another. They have a bit more freedom than the nice, neat rows and columns here in this solid. When you get to the gaseous state, these molecules are now very far apart. In fact, you would assume, and you might know this from the gases chapter, you might assume that the intermolecular forces in a gas are zero. The molecules are very far apart. They really can't get close to one another to touch and have those interactions. So as we're moving from left to right here, we are decreasing strength of our intermolecular forces. The molecules are getting farther apart, they're getting faster, and so they are less likely to have that positive, favorable interaction together. As we move from left to right, we're also breaking intermolecular forces. And in terms of a phase change, if you think of this in your kitchen, right, you have some ice and you want to melt it, right, you need to do that by input of heat. If you have some liquid and you need to boil it, you need to do that again with input of heat. So we are breaking these intermolecular forces by adding heat to the system. So that's the sort of introduction to intermolecular forces. Let's go through a free response question now from the Princeton Review, and let's take a look at what we might be able to figure out here. So this first question asks you to consider the Lewis structures for the following four molecules. They tell you that all of them are liquids at room temperature. That's hard to predict off the top of your head. And I want you to organize them from high to low in terms of boiling points, clearly differentiating between the intermolecular forces in each substance. So let's go with that last part first. Let's differentiate the intermolecular forces in each substance. Let's figure out what's present and what's not. And I'm going to go in order of strength. Because the stronger ones are going to tend to be more important. So the first thing I'm going to look for is hydrogen bonding. All right. If I take a look at pentane first, for example, here on the bottom left, pentane is made up of carbon-carbon as well as carbon-hydrogen bonds. Those, I specifically mentioned those earlier, those are very non-polar. It doesn't fit that really rigorous specific requirement for having hydrogen bonding or experiencing hydrogen bonding. So pentane is not going to have hydrogen bonding. Methanol, on the other hand, has an OH group. That OH group is going to be able to participate in a hydrogen bond. So I'm going to highlight that in red to correspond to the red H bond over there on the left-hand side. Similarly, this NH2 group is also going to be able to hydrogen bond. N was one of the atoms that can be involved in a hydrogen bond, so that's a possibility. And propanol, the top right here, has an oxygen atom. That oxygen atom may be able to hydrogen bond. The problem with that is it can't hydrogen bond with other molecules of itself because there are only CH bonds in there. So that could maybe hydrogen bond with butylamine, but it can't hydrogen bond with itself. The next one down was just your plain old dipole-dipole forces, right? So I'll do these in blue. And dipole-dipole forces showed up anytime you had polar molecules. That was the only requirement for them. Pentane, CH bonds are very nonpolar. That's about as nonpolar as it gets. But when you get to methanol, you're going to have a big dipole between that carbon and that oxygen in methanol. So you'd expect dipole-dipole forces to happen as well. Similarly, in propanal, you're going to have these carbons near that very electronegative oxygen atom. So you'd expect dipole-dipole forces to show up in propanal as well, and as well in butylamine. Now, the further you get away, I've highlighted just this first carbon next to the nitrogen in blue here. The further you get away, the less polarized the electrons are going to be. These carbon atoms over here don't really see the nitrogen as much as this carbon in blue, so it would be difficult for them to have a sort of significant contribution to the dipole-dipole formation there. Last but not least, necessarily, we have London dispersion forces. This is going to be present in all molecules. So really all of these should be green, but I'm really just looking at the most important parts of it. Pentane does not have any polar bonds. The only intermolecular force it really has going for it is our London dispersion forces. So that's all green. Here for butylamine, like I said, this part of the chain is probably not going to be very polarized. So that green portion of the chain is going to experience those London dispersion forces, right? So these are the types of things you need to be able to do for these AP questions. Obviously, you can't really highlight like this when you're taking the exam, but it's important to be able to identify what these different forces are based off of those strict rules that I showed you on a couple of previous slides. So let's go ahead and rank these now, right? So the weakest of all of these is the London dispersion forces, and so pentane, which is really just all London dispersion forces, it doesn't have anything else going for it, is going to be the weakest intermolecular forces. So I'll write that below here. Pentane is going to be experiencing the weakest intermolecular forces. The strongest intermolecular forces is probably going to be one of these two because those both really participate with themselves in hydrogen bonding. If you just look at the colors, right, they both have red, they both have blue, so those are a little bit of a wash. But butylamine, because it has this extra group attached that methanol lacks, it's a little bit heavier, it's going to have higher London dispersion forces. That is going to actually be the compound here with the strongest intermolecular forces. It experiences hydrogen bonding. It is also the largest molecule here. So both of those sort of point to this having the second strongest the strongest intermolecular forces. Rounding out this discussion here, methanol, which has the best ability to hydrogen bond of the remaining two, is going to have our second strongest. And then finally, propanal is going to be the third strongest. It's always easiest to find the extremes, the strongest and the weakest. The middle two are maybe a little bit more challenging. So we've differentiated the intermolecular forces. We've differentiated the strengths. The final thing we have to do is connect the strengths of these intermolecular forces to their boiling points. And I'm going to go back a couple of slides just to make sure we take a look again. When we are boiling something, right, we're taking it from the liquid state to the gaseous state. And as we move from left to right on here, we are breaking those intermolecular forces, right? When we boil a molecule, when we boil a sample, we're taking those liquid molecules and pulling them apart. We're putting them far apart in the gas phase. We are literally pulling against those intermolecular forces. So the stronger the intermolecular forces, the harder this process becomes, the more energy I need to put in order for that compound to boil. So if we're looking at the compound with the highest boiling point, you would want to follow the general rule, which I'll type out here. Higher intermolecular forces means higher boiling points. Right? The higher the intermolecular forces are, the harder we need to pull to get those molecules apart into the gaseous phase. So the strongest intermolecular forces here, butylamine, is also going to be the one with the highest boiling point. So strongest intermolecular forces and the highest boiling point. You guys can fill in what the weakest, how the weakest intermolecular forces would correlate to the lowest boiling point as well. One more thing here before I move on. So I'm saying that the higher intermolecular forces correlate to the boiling point. But if we go back to this diagram again, whether I'm moving from liquid to gas, so I'm worried about boiling, or whether I'm moving from solid to liquid, so I'm worried about melting or fusion, the official scientific term, I'm still breaking apart those intermolecular forces. So intermolecular forces are going to have an effect on the boiling point as well as the melting point going from solid to liquid. So I'll put that on the slide as well, that when we're ranking these intermolecular forces, they are going to correspond to both the boiling points and the melting points of these compounds. So whether the AP, if the AP asks you about either one of those, you approach the answer in the same way. The other free response question for this one, I'm not going to do. I wanted to make sure that we got this one in. I think this is the most important type of intermolecular force question because it forces you to do two things. It forces you to assign intermolecular forces, like we did with the different colors, and it requires you to rank intermolecular forces. I guess three things. It then requires you to take those intermolecular forces and predict physical properties with them. I've seen a lot of intermolecular force questions, and most of them come down to those same three things: knowing what the intermolecular forces are, being able to rank them, and being able to correlate them to different types of physical properties. So if I were writing an exam question, those would be the types of things I would focus on for intermolecular forces. Big important topic. We're going to move on though to another big important topic. We're going to talk about chemical reactions. That was another one of the topics that we're going to be talking about today, right in the middle of those units. All right. So if you guys have any questions, please feel free to pop them in the chat, and Tyler will pass them on over as appropriate. But we're going to leave intermolecular forces behind, and we're going to move into different types of reactions. This is a long list of reactions with sort of in-depth definitions for some of them. So I don't want to spend too much time on this, and I don't want you guys to spend too much time on it either. These are the types of things that if you really needed to, you'd be able to look up these definitions maybe in the heat of the moment on your AP exam. There's going to be 6 different types of reactions here, and we're going to focus on one of them today. First is a synthesis reaction. That kind of sounds like what it is. You take two things and you smush them together to make one thing out of it, or three things to make two things out of it. You synthesize compounds by combining other molecules or atoms. Decomposition, they say here, is just the opposite of synthesis. If you go back the other way, you take a compound and you break it apart into its constituents. So mercury oxide here gets converted into mercury and oxygen. This often happens in the presence of heat. If things decompose in the presence of heat, this is a candidate for the type of reaction that's occurring. Acid-base reactions. So acids and bases are one of the units that are off of the AP, so you don't need to spend any time on this. But note that the definition of acids and bases is related to protons and proton transfer. HCl here has a proton, and that's a strong acid. You guys will learn more about that in college if you don't end up testing out for whatever reason, though. Fourth, here we're going to talk about redox or oxidation reduction reactions. Which result in the change of the oxidation states of different atoms involved. We're going to talk about these in more detail, so I'm just going to move on and we'll get back to those. We'll finish up with the other types of reactions here. This is specifically hydrocarbon combustion, but in general, combustion reactions are reactions in which something combines with oxygen. If it's hydrocarbons, it's nice because you have these predictable products, and there's a lot of stoichiometry and a lot of enthalpy types of questions involved with combustion reactions. Finally, here you also might see precipitation reactions. Precipitation reactions occur when you have two soluble species which react to form at least one insoluble species, right? So in this case, magnesium carbonate is an insoluble salt, and so that would precipitate out as the solid. Solubility rules are a good thing that you might want to put on your crib sheet. There was a question about that earlier. Solubility rules are something you would want to write down or have easy access to rather than memorizing, because those can be a little difficult to memorize in my experience, because there's a lot of them. These are all the different types of reactions. You're going to want to be familiar with all of these. Like I said, acid base is off. We're going to focus on the redox reactions today. I think those are probably the most difficult, the most unfamiliar, and they have the most to do in them. All right, so we'll spend the rest of the time today talking about redox reactions and going through some free response questions, maybe some kinetics if we have time for it. So oxidation reduction reactions, as we noted earlier, as it was defined on the previous slide, are characterized by having a transfer of electrons. And the way we determine whether electrons have been transferred is by assigning oxidation states. Now, I'm not going to spend time talking in detail about how we assign oxidation states. That's something for you guys to look up. There's a set of rules that if you wanted to, you could put on a crib sheet. But I'll just run through and quickly determine it here. So if we're taking a look at this reaction right here, we start off with iron. And this is just an iron atom with nothing else attached. So it's its elemental form. Any atom in its elemental form is going to have an oxidation state of 0. For HCl, H and Cl usually take predictable oxidation states. H tends to be +1 and Cl tends to be -1, so that's pretty straightforward. Over here on the other side of the reaction, H2, this is the elemental form, right? It's just hydrogen atoms, there's nothing else attached, so this is going to be in the 0 oxidation state. Chloride, again, has the predictable oxidation state of -1. And since there are two of them, that tells you that the oxidation state of iron in the products is going to be a +2. So you want to follow, I'll help you follow along with the colors here. We start off with this green iron 0, and we end up with green iron 2 plus. We start off with, excuse me, let me use a different color. We start off with blue H plus 1, and we end up with blue H0. We've changed oxidation states, and therefore this is a redox reaction. Okay, so let's look a little bit more in detail and assign what actually has taken place here, because it's important to be able to look at a reaction and determine what's been reduced and what's been oxidized. There's a couple of mnemonics here that can help you, along with the specific sort of scientific definitions. The definition of an oxidation is a loss of electrons. If you lose electrons, your charge and oxidation state is going to increase. So taking a look back at this reaction, iron 0 lost 2 electrons to become iron 2 plus. So this is an oxidation reaction. The opposite of oxidation is reduction. In a reduction, you gain electrons. There's a lot of confusing stuff when you're talking redox, and that's probably the most confusing thing, that a reduction is a gain. You're not reducing the number of electrons, right? You're gaining the number of electrons. What's actually being reduced here is the charge or the oxidation state, right? Electrons come with a negative, so if something gains electrons, their oxidation state or charge is going to be decreased. And that's what's happening here to hydrogen in HCl, right? It's starting as +1, and it's being converted to 0. That oxidation state slash charge is decreasing. That means it must have gained electrons. Therefore, this has been reduced. In any redox reaction, you have to have oxidation and reduction together. Oxidation, loss of electrons; reduction, gain of electrons. It's really just a transfer of electrons. You can't have one without the other. It's important to make sure you have those definitions memorized and can apply them. There's a couple of mnemonics they give you guys here. Leo says "gur." I don't like this mnemonic personally. A lot of people use it, but if I had to spell the sound that a lion makes, I wouldn't spell it GER. So that I've never found too helpful. I do like this other one though, oil rig. Oxidation is loss, reduction is gain. The initials spell out the term oil rig, and I just want to specify here that when we're talking about the loss and gain of these things, in this specifically, it's loss and gain of electrons. One way or the other, you have to memorize that. Oil rig, like I said, is my preferred way. We're going to talk next about reduction and oxidation potentials. The way we're going to use these potentials is we're going to use them to measure the favorability or the likelihood of a reaction. So they're not exactly the same, but in this case, they work out to be the same. So it's a measure of the favorability slash likelihood of reaction. That's what these numbers are going to be good for. So let's take a look at a reaction here. And this is just a reduction reaction. I mentioned on the previous slide, you can't have reduction without oxidation. They have to go together. Here, we're only looking at a half reaction. And this is very common to see half reactions where you're only shown either the reduction or down below here an oxidation in order to do analysis of them separately. So this first reaction here is a reduction half reaction. Reduction of zinc 2 plus, it would gain 2 electrons to become zinc in the solid form. And its reduction potential here, which is given the letter E, is going to have a value of negative 0.76 volts, right? You might know from your physics side of things, if you're taking AP physics, that voltages are a measure of of predicting how electrons move, more or less, right? So we express the favorability of this electron transfer in volts, not too surprisingly. So this reduction reaction has a reduction potential of that number right there. We'll talk about it in a second, a little bit more what that number means. But down below, let's take a look at the corresponding sort of twin reaction to this, or mirror image reaction to this. You know that the top reaction here and the bottom reaction here are just reversed, right? So we're proceeding forward here, we're proceeding in reverse for the second one. So the top is a reduction, the reverse would be an oxidation reaction. Zinc 0 is going to be losing 2 electrons to become zinc 2 plus, just the opposite of the reaction above. And not too surprisingly, the oxidation potential for this, which is a measure of the favorability, is the opposite of the reduction. We'll talk more about the signs here, but if you start with one reaction and you reverse its direction, if you want to get the potential for that reversed reaction, you just take the negative of that potential to get it. So that's the connection between these first two. And they give you this very important relationship here. So I'm going to highlight this. The larger the potential for a half reaction, the more likely it is to occur. To be a little bit careful with this, larger is maybe not quite specific enough. When we're saying larger here, what we're really looking for is the more positive potential. Right? So let's take a look at these two reactions here. Well, the oxidation potential is positive 0.76. The reduction is negative 0.76. The more positive ones are going to be more likely to occur. So I would take a look at this reaction right here and say, well, this one with the positive value is the one that is going to be more likely or more favorable, right? At least of these top two reactions, the oxidation of zinc is more favorable or likely than the reduction of zinc 2 plus. Let's take a look at these last two reactions here. Zinc is a little bit hard to predict off the top of your head, but these next two, fluorine and lithium, you should be able to sort of follow along with this by taking a look at the periodic table, if nothing else. Fluorine here gaining 2 electrons. Well, let's think about how much fluorine wants to gain electrons. There's a lot of different ways you could do that. It's the most electronegative element. You can think of it as it wants to gain 1 electron to achieve its noble gas configuration, right? It has the highest ionization energy. There's a lot of ways that you would be able to figure out that fluorine really wants to gain electrons. Not too surprisingly, the reduction potential here is a positive number. Positive means favorable. The values in these numbers, they rarely exceed 3. So the fact that this is like almost 3, it's positive 2.9, that's really high. So that's something that this is a very, very favorable reduction. On the other side, if we look at lithium, well, lithium is way far on the left-hand side of the periodic table. It really likes losing electrons to achieve a noble gas configuration. So not too surprisingly, it has a very high oxidation potential, a very high positive oxidation potential. If you were to reverse this reaction, right, lithium plus would gain an electron, and that would have a reduction potential of -3. That would be extremely unlikely, extremely unfavorable. And that's sort of what we observe, right? You don't see a lot of lithium around, but you're probably familiar with a lot of lithium salts, right? That's mainly how we experience it on Earth. We don't find much of this because it's very reactive. It really wants to liberate that electron, it really wants to get oxidized to become lithium plus. If you guys have any questions, please feel free to pop them in the chat. I'd be happy to help out. The information on this slide just deals with either reduction or oxidation potentials. So we can take a look and say this reaction is better than this one. This reaction is not as good as this one, etc. But these are only half reactions. They only tell us about that one half we're looking at. What I want to take a look at here before we get into doing some questions are what happens if you smush these reactions together. So down below here, let's say we take this oxidation reaction like we just saw on the previous slide, and we're going to couple it with this reduction reaction. So the electrons that come from zinc are going to get soaked up by the silver ion here to get this net reaction, this net redox reaction, okay? And we want to say, well, we know how favorable the oxidation is. We know how favorable the reduction is. What about when we put them together and we smush them together? How favorable is that overall? Luckily, it's a very simple way to calculate it. That if you want to figure out how this works overall, how well it works overall, if you want to get the E value for this reaction right here, you just add up the individual constituent E values. So you take the oxidation value, which would come from this zinc reaction, and you would add it to the reduction potential, which would come from this silver containing reaction. Add those up and you get this overall value of plus 1.56, right? Not too surprisingly, right? These are both positive numbers. That means favorable. When you put them together, you get an even more positive, even more favorable reaction. These are two really good reactions, so they overall make a much better reaction. Fadi's asking a really great question. Is there a way to predict reaction potentials? That's a really hard question. That's a really hard thing to do. A lot of times what it comes down to are electron configurations. So if you needed to, you could figure out the electron configuration of zinc and zinc 2 plus and say, well, the configuration of zinc 2 plus is pretty favorable. Therefore, it would be a favorable oxidation reaction. You could look at this reaction below and you would, if you were to predict the electron configuration of silver, you would find that it's a very special, stable electron configuration, whereas silver plus is not especially stable or favorable. Therefore, its formation is going to be a favorable process. So, Fadi, if you need to predict reaction potentials, the best way to do it is to look at the electron configurations of all the species involved and then make a judgment about which of those configurations is most stable. It is a difficult thing to do. It does involve a little bit of hand waving and guesswork. Aaron is asking, is applying reduction potential of voltage to the activity series, is that going to be fair game from the exam? If that's how if that's how I'm interpreting it. So, Aaron, I believe you're saying that the activity series is going to be in unit 9. So let me read your question more carefully. Sorry, it's understanding. You know what? I don't know for sure off the top of my head where the activity series falls in the units. So I can't answer that question because I don't know where the activity series is. There is a connection between those topics, but if that activity series is part of Unit 9, the applications of thermo, then I would expect it to not be on the exam this year. But I don't know what unit it's in off the top of my head. I'm sorry about that. I want to get into the free response question so we can apply some of this. But before we do that, I want to point out something extremely important here. You never multiply the potential for a half reaction by a coefficient. If you note here down below, in order to make the number of electrons in and out work out, we had to multiply the silver reaction by 2, right? That's where the 2 comes from in the net reaction here. But when we did the math, we did not carry that multiplied by 2 into the math. Let's make this clearer, right? What we did here is we had to multiply the silver reaction by 2, but this 2 does not appear here, right? We don't multiply the 0.8 by 2. I think that's counterintuitive. I think most people would, if you didn't know, would assume that you should multiply those, but you should never multiply them. And it's because of the units. Volts is joules per coulomb. So if you have more coulombs, well, you have more joules, but the units work out such that it doesn't scale like that. So you never want to multiply those potentials by a coefficient. And if this is the type of question that's going to show up on the AP, I have to imagine that that's probably the most common way for students to lose points there. Graders are going to be expecting that, so make sure you don't do that. It is counterintuitive, so you do need to maybe stop yourself from doing it. But if you look at it this way, right, it makes your life easier. You have to do less math if you keep in mind this extremely important yellow information. So we got the basics of these of this redox stuff happening here. Let's go ahead and take a look at a free response question to sort of put some of this together. All right. So this free response question here is showing us what they note is an unbalanced reaction between potassium permanganate, this species here, and acidified iron sulfate. There's the iron sulfate, iron +2. The acidified is the H+, but that's not on the exam, right? This is asking us to provide the equations for both half reactions that occur below, both the oxidation and reduction reactions, and then the balanced net ionic equation, meaning put the half reactions together. So let's go ahead and figure that out here on my my slide. First thing I'm going to do is I'm going to figure out the oxidation half reaction. Now I have to, I have to dig a little bit. I have to assign some oxidation states potentially, but iron 2 plus on the left here gets converted to iron 3 plus on the right. That's an increase in your oxidation state. It lost electrons, so that is going to be my oxidation reaction. Now the atom is balanced here, right? One iron is one iron, but the charges are not. The charge here is +2, the charge here is +3. In order to balance out those charges, I'm gonna have to add an electron to the right-hand side because now the charge is +3 minus 1, which equals +2. Whenever you're writing these half reactions, you always have to have electrons in there. If it's an oxidation reaction, electrons are gonna be your product. In a reduction reaction, electrons are going to be your starting materials. So that's our oxidation reaction in red. The remaining species must therefore be involved in the reduction reaction. So let's take a look at that in blue. I've got H plus. I've got permanganate. And all of that is being converted to manganese 2 plus, as well as H2O. And I don't care about phases here. So I'm going to need to balance this reaction out. I'm going to balance it like normal. I would start by balancing out the the amount of oxygens. So I need 4 on my H2O. I now have 8 protons, so I'm going to need an 8 protons on the other side. And at this point, all the atoms are balanced. I do need to balance out the charge, however, and I'm going to need to balance out the charge. Sorry, I'm running a little short on space here. I'm going to need to balance out the charge by adding electrons to my starting materials. This is a reduction reaction, which means that electrons are going to be gained. And so I need to have electrons as starting materials. I'm going to need 5 electrons in this case because that's how the charge balances out, right? The left-hand side has a charge of 8 plus, 1 minus, so that's 7 plus, minus 5 is 2 plus, 2 plus is the charge on our product side. So when we're writing out these half reactions, we need to make sure that both of those are going to be balanced. Now, the other part of this question was to write the balanced net ionic equation. So we're going to write that balanced net ionic equation just by adding these top 2 equations together. But before we do that, we need to make sure that the electrons cancel, the electrons balance as well. In my oxidation reaction, each iron atom is only losing 1 electron, but in my reduction reaction, 5 electrons are being gained. What that means is my oxidation reaction has to happen 5 times for every time my reduction happens to make sure that the electrons balance out. All right. So I'm going to add these together, and red plus blue makes purple for my net reaction. My net reaction is just going to take all the species from the starting materials from above. So I have 8 protons. I have a permanganate. I have 5 electrons. And I have an iron 2 plus atom. That's all my starting materials. And now I'm going to add up all the products as well. So I'll end up with iron 3 plus. Sorry, I forgot to carry through those coefficients, right? The iron should be multiplied by 5 because I had to distribute that 5 in to the electrons as well as the iron species. So I've got 5 electrons on the right hand side. I've also got manganese 2 plus and 4 H2O molecules. This is what the net reaction looks like initially. What I'm then going to have to do is cross out things that cancel out. So for example, my 5 electrons cancel out on either side here. It's not just the electrons which have to cancel. Other things could, but in this case, it's only the electrons that cancel, and that's going to give me my balanced reaction after I eliminate those electrons. So I got the 2 half reactions here, my oxidation, my reduction. I smushed them together to get to the net reaction. The next thing the AP exam is asking me to do, I'm sorry, I think I might have, okay, there we go. This went a little bit out of order. The next thing the AP exam is asking me to do is to predict some color changes. And they give me some information to do this. I don't have to know any of this information off the top of my head. They note that different ions have different colors, and they want you to describe the color of the situation at different points in this titration reaction here. The titration reaction is just the chemical reaction that they wrote above, and they give you the different colors of some of the different species here. So for example, tell you iron 2 plus is this sort of pale green color, not exactly the color of my highlighter. They tell you that permanganate is a deep purple, which I could possibly do here. Here we go. It's definitely not that color. The color of permanganate is extremely deep purple. You should Google it. It's a pretty color. Manganese 2 plus on the product side here, they tell me is colorless, right? So I wouldn't observe any color from that. But they do tell me that iron 3 plus is a yellow species, right? So those are the different colors involved. And they want to see how the color is going to change in the course of this titration. Well, in this titration, let's read here. They tell me that a solution of this purple potassium permanganate is placed in a burette before being titrated into a flask, which contains this iron 2 sulfate, right? This iron 2 sulfate is green, right? And the product of it is that yellow stuff. So let's take a look at the situations here and see if we can describe the color. I've already kind of done the work for us up above. What is the color of the solution before the titration begins? Well, before the titration begins, it's just that iron sulfate, right? We haven't added any of the potassium permanganate. So before the titration begins, we're just going to have that green iron 2 sulfate in there. During titration prior to the endpoint, right? The endpoint is when these two things have completely reacted with one another. So before we've hit the endpoint, we're still going to have at least a little bit of that iron 2. So at least somewhat in that in this reaction here. Before I have the endpoint, if I still have iron 2, I'm still going to have a little bit of the green there. But as that iron 2 reacts, it's being converted into this yellowish iron 3 plus. So I'm going to have a little bit of yellow. I'm also going to have a little bit of green in there. Maybe I mix them together to get a little bit of a green yellow color. It's a little bit tough to predict exactly, but it would be a combination of those colors. Finally, let's look at the end point of the titration. The end point is the point at which all of these things have completely reacted with one another. So that means there's not going to be any of this green iron 2 left. So I'm not going to use the green here. I will have iron 3 plus though present, right? I'm going to have the products present at the end point. And depending on how careful I am, I might have a little bit of this potassium permanganate in there, right? If you've done a titration in a lab, you have to go until you see a little bit of that color remain, most likely. So you might also have a little bit of the purple in there, I'm not sure what color purple and yellow make when mixed together, but you might be able to see a little bit of both in there depending on how well the mix is. These types of experimental lab-based questions tend to show up on the AP, and so I think it's important. This is not something that's very generalizable on this question, but I think it's important that you are able to deal with this type of experimental data that they give you. So I believe the last free response question we're going to be dealing with today, just checking on that, but maybe the last, second to last, maybe, is a math question. And I noted in the last live stream, I didn't have it on this one because there was a problem with the image, that math is something that is heavily tested in the free response question, heavily weighted, up to about 50%. So you're likely to see a math question here. So let's take a look at this. And this is now just an old school stoichiometry question. So probably some of the very first stuff you did in your AP class, going back very early in the year. They want you to figure out that if you have 15.5 mils of the titrant, what is the initial concentration of the iron sulfate? The question essentially boils down to, how much of this you have, how much of this does it react with? So it's really just flexing a lot of your stoichiometry muscles that you might have not been working out on more recently, because this is probably something that's a little bit older here. So let's take a look, and let's take a look at the balanced reaction, because if you're doing stoichiometry, you need a balanced reaction, and try to make that correlation. All right. So the thing we started off with here was we started off with the amount of this potassium permanganate solution they gave us was 15.55 mils of that potassium permanganate. All right. Now I need to convert the milliliters of this, right, to the concentration of that. So at this point, it's just a lot of unit conversions. And I know everybody does these a little bit differently. I hope you can follow along with how I'm doing it. First thing I'm going to do is I want to convert this to moles. And so I'm going to do that by canceling out the milliliters and saying that for every 1,000 milliliters, I know that I'm going to have 0.15 moles, right? It's 0.15 molar, which means I have 0.15 moles per liter of solution. So for every 1,000 milliliters or 1 liter of solution, I'm going to have 0.150 moles. Right? So that tells me the amount of moles of potassium permanganate I've added into this reaction. I can correlate that to my moles of iron 2 by noting from the stoichiometric coefficients that for every 1 permanganate ion I have, I need 5 iron 2 plus ions to react with it. Right? So if I do this math and stop at this point, my answer is going to come out with units of moles of iron. But they're not asking me for moles of iron, they're asking me for a concentration of iron. Concentration of iron is going to be moles per liter, right? So I'm going to take this and convert it to a molarity, moles per liter, by noting the volume of the solution. I start off with 50 milliliters of iron, and so that's the value I'm going to need to plug in here to get my molarity. I'm going to convert that to liters. It would be 0.50000 liters. Now that's too many zeros for the calculation, right? You don't need all of those, but we'll see very shortly that significant figures are going to play a role here. So we do need to note the actual number of units, digits that we have. You can go ahead and plug this into your calculator, and what you're going to find is that this is a 0.233 molar solution of iron 2 plus. Now it is 0.233, and there are 3 significant figures in there, and I'm tracing those 3 sig figs back to this right here, the molarity of the the permanganate they gave me in the question, which has 1, 2, 3 significant figures in it as well. There's 3 there, so that's the amount of sig figs I need in my answer. Note that just counting and definitions like that, you don't worry about sig figs. So this would be the calculation for figuring out the concentration of that iron 2 plus. The next part of this, they tell us that the actual concentration of iron is 0.25. Then I want you to calculate the percent error. For the purposes of time, I'm not going to calculate that percent error, but I do want to note that this concentration is too low. And I want to figure out why, because on the next slide, the next question that they ask you is to detect the sources of error, which is the type of thing that shows up a lot on AP. So we want to figure out if these errors would lead us to this deviation, meaning our concentration being too low. Let's try to figure that out. So for E1 here, they say that instead of the 50 mils they quoted us in the question, it's actually 55 milliliters of iron sulfate. So the volume of the solution was higher than we calculated, right? The volume is sort of, what that means is our volume is artificially low. Let's take a look here. Where did that number come in? Well, it came in right here on the bottom, right? So if this number is artificially low, that means the answer is going to be artificially high, right? If our denominator is too low, our numerator, the answer, is going to be too high. So for that first question here, no. And the reason is because this would increase the concentration of iron. Right? It says specifically to justify your answers quantitatively. I interpret that as pointing at an equation. If this number is too low, this number is going to be too high, but we figured out that our answer was too low. So that would not explain the direction of the error. The next thing they say is the concentration of potassium permanganate was actually 0.16. They quoted it as 0.15, but in reality, it's 0.16. Let's see how that would affect it. Well, this 0.15 is in our numerator, right? This number apparently should have been a 0.16, which means our numerator is too small. If our numerator is too small, the answer is also going to be too small. So yes, that could explain the direction of the error that we're getting here. So this would explain that, because this would deflate our concentration of iron 2 plus that we calculated. You see these explanation of error questions a lot. I think the best way to approach those is to try to plug them into an equation. I think that's the most straightforward mathematical way to solve it. They even specify this when you need to use math to solve it, so that's doubly true for that one. So that's all the time we have for today. This is we got through the intermolecular forces, we got through redox reactions. We didn't get to kinetics, but that's something we can talk about in the next live stream. And just to sign off with that, the next live stream session for AP Chem is going to be Friday, May 1st at 1 p.m. Eastern. That's a time change from this session. We'll talk about a little bit of thermo, a little bit of equilibrium, and we'll also touch on some kinetics, which we weren't able to get to today. Hope you guys are doing well. Hope everyone's preparing still for their AP exams as normally as possible. Hope everyone is staying safe and healthy. And I hope to talk to everyone again on Friday, May 1st at 1 p.m. Thank you, guys.